So in today's lesson, we are introducing the concept of a system of equations. This is a topic you guys would have learned about in Algebra 1 and spent a decent amount of time then learning the different ways to solve a system. In Algebra 2, we're going to cover those same methods you learned before, but we're also going to build on them and make them more difficult and more complicated than they were in Algebra 1. So we'll get into that later, but this lesson is kind of reviewing something that should look kind of familiar. A system of equations looks like this, and all it is two or more equations jumbled or bunched up into one package. You usually use like a squiggly guy like this to show that these are both part of the same problem. So a system of equations is just a package of multiple equations. So a package of multiple, meaning two or more equations. And the first thing we're going to talk about with regards to a system is what it means to be a solution. And to be a solution to a system of equations, you have to work in every equation in the system. So for this problem right here, if I'm a solution, I have to work in this problem, and I also have to work in this problem. And what we're going to do right here is just test a couple points that I give you and see if they're solutions or not. All that means is we're going to plug in our points. So they give us an x and a y on our coordinate here. And what we're going to do is plug the x in for x, plug the y in for y, and see if it does equal 30 like it's supposed to. So what I would do is I would plug the 3 in for the x minus 6, and I have to see if this actually equals 30 like it's supposed to. Okay, so I plugged x, I plugged y. If you do the math on this, this is going to be 6, and negative times negative makes this a positive 24. So that does equal 30, and it worked in the first equation. Just because it works in the first equation doesn't mean it's a solution by itself. It has to work in every equation in your system. So I'm going to take that same coordinate and plug it into this other equation. This one starts out with a y equals, so I'm going to put negative 4 equals, plugging negative 4 in for y. And then it's supposed to go x minus 1. On this one, though, I'm not going to get the right answer. It did not work out. So is this point a solution? You have to make everybody happy to be a solution. The top guy is happy. This one is not. So this is not going to be a solution to the system. It's a solution to this equation, but not to the whole package. Okay, let's go on to our second point. They give you a 10, 9, and I'm going to go ahead and plug 10 in for x. And I'm going to plug a 9 in for y. And if I do that, that's going to be 20 minus 54. Clearly doesn't equal 30. That's not like negative 34. Since it already didn't work there, I'm not going to waste my time plugging it in the other one. I already know it's not a solution. And I give you one more point here to plug in. And negative 6, negative 7, starting with my first equation, I would do 2 and then the negative 6 minus 7 and then negative 7. Wait, hold on. Sorry. This is a 6, negative 7, so it's 6y, equals 30. And when I do that, I'm going to get negative 12 plus 42 equals 30. Cool, yeah, that works. And then on my second equation, I have to do negative 7 equals negative 6 minus 1, which does equal negative 7. So it works in both. This is going to be a yes. So if I give you a coordinate, you should be able to tell me if it's a solution or not by plugging it in. But if you guys can kind of pretend like this wasn't here and I just said, oh yeah, solve that problem for me, this is a really, really bad method to solve a system. It can verify if something is a solution, but picture if you just kept throwing things at this equation, picking different numbers for these until you made the problem work. It's just not a good way to do it. So in Algebra 1, you learn 3 different methods for solving a system. Today's method is solving by graphing. So what I want to do now that we can understand what it means to be a solution is solve this exact same problem like the real way. Because if you look at this, I had to give you the answer before you could verify that it was true. So this is like if we saw the same problem from scratch. What I'm going to do is graph both of these equations on the same grid. So I'm going to start out with my blue equation right here. And if I do that, it's going to say negative 2x and positive 30. I'm going to divide by negative 6 to everybody. that top equation ends up being y equals, that'll reduce to 1 over 3x minus 5. So I'm going to go to negative 5 on my graph, and I'm going to go up 1 over 3. Normally I would just draw a line and be done, but I'm going to keep counting up 1 over 3, up 1 over 3, and I'm going to make as many dots as I can that'll actually fit on this picture. When you solve a system by graphing, you need to do lots of dots, not just the bare minimum like you would on a single graph. So if I do all that and I connect them, I get this blue line right here. The thing about a graph is it shows you all the points that work in the equation. Every point in blue, and even these like decimal points in between, if you plug in those coordinates for x and y, it makes the problem work. Everything on the blue graph works in the blue equation. Well, on that same picture, what I'm going to do is I'm going to graph my green equation. Now, my green equation starts at negative 1, and it has a slope of positive 1, so I'm going to go up 1 over 1, up 1 over 1, up 1 over 1 like that. And I could keep on going right here, but if I'm going to be smart about it, they're not going to cross over here. What we eventually do is we look for where they cross. So I'm just going to go the direction that the answer is actually going to be, carefully counting as I go until I find that dot. So I'm going to draw in my second equation right here, like this. So all the points on the blue graph work in the blue equation. All the points in the green graph work in the green equation. There is only one point that works in both equations, and it's where they cross right there. And the coordinates of that, if you look, are negative 6, comma, negative 7. Okay, so the solution to this problem, the only place where they cross, is negative 6, comma, negative 7. Write this down as a note for yourself here when you do these. Strategy is graph everything, and after you graph everything, you have to give the intersection. So the intersection is where they cross. People will sometimes graph them and forget to actually say the answer, but the answer is where they cross each other. So now that we've done an example, you guys could do more problems like that, and it would be cool. But I think you guys probably get the idea with graphing here. I want to talk about how many solutions a system can have. And I specify here that it's a linear system, so each of our graphs is going to be a line. We already saw one scenario. Like, let's say I graphed my lines when they were like this, or you can look at the last example as well. Sometimes when you graph a system with two lines in it, you have one solution. Okay? This is when you have intersecting lines. So if your lines intersect each other, like most of the time they will, you're going to have one solution to your problem. See if you can think about another situation here. So pause my video. In class, I would ask you guys to tell me what these two are. What else can happen when you draw two random lines besides having one answer? Okay, so think about that for a second, because I'm about to say the answer. Another possibility here is that your lines actually run parallel to each other like this. If you graph your system and you get something like this, well, those lines aren't ever going to cross, so there are zero solutions or no solution. Okay, so if you graph your lines and they're parallel, well, they don't cross, they don't have an answer. That is parallel lines. So when your lines are parallel to each other, you're going to have no solution to your system. And the third situation is, what if I had a line like this and I had like a second line right over the top of it like that? So the two lines were actually on top of each other. This is called infinitely many solutions. So what you would say for your answer is that it's infinitely many solutions. In an earlier video, I did an all real numbers. That's not the same thing. This is not all real numbers because there are points like here, 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 here that don't work. So you can't say it's like literally everything, but everything on both lines is going to be a solution. So infinitely many solutions is the wording you need. And the lines, when they're on top of each other, are called coinciding lines. So lines on top of each other are called coinciding. These are the three things that can happen when your system is linear. Now, in Algebra 1, we lived in linear system land, and this is all we ever did. But in Algebra 2, we're going to talk about a lot more complicated types of systems with other equations in them. As of now, we only know about one other kind of equation. We're going to learn about a bunch more this year, but it's our good friend, the absolute value. So this is not a linear system. It's not just a line. So these three scenarios right here won't apply. We kind of just have to graph this and see what happens. So my first equation I'm going to make blue. It's an absolute value, and I need to count left 1, down 4. That's going to be my vertex, left 1, down 4. Slope is up 2 over 1. And remember, guys, whenever you do a systems problem, you need lots of dots. Don't be stingy on your dots. It makes it easier to see where everything is going to eventually cross. So tons of dots here. Honestly, I should have done even more, but they're not going to cross up there. I already know where the answer is going to be. So just do as many dots as you can. And then my second equation is going to have, I'll make this one green. This guy is linear. So I'm going to start at -2, and I'm going to count down 2 over 3. Down 2 over 3. And I can keep going this way, but obviously that's not helpful. So I'm also going to reverse it and go up to left 3. Now what you're going to find in this problem is that we don't just have one answer, like a linear problem. This problem actually happens to have two answers. They cross right there, and they also cross right there. Both of those are going to be solutions. Those are the points, -3, 0, right there. And right here, it's 0, -2. So you kind of just have to graph them and see how many answers there were. If I had this same picture right here, but my linear graph went like that, it could have been where there was no solution with blue and orange. So you could have a no solution. You could even have it cross like here, where perhaps there's only one solution. You kind of just have to graph the problem and see what happens.